Okay, so now that we've gone through the steps of hypothesis testing, let's do an example. So this is going to be a two-tailed test example. I do also have a one-tailed test example for you guys to see as well. So let's start off here. Our problem is a national business magazine reports that the mean age of a retirement for women executives is 61. A women's rights organization believes that this value does not accurately depict the current trends in retirement. To test this, the group polled a simple random sample of 95 recently retired women executives and found that they had a mean age of retirement of 61.5. Assuming that the population standard deviation is 2.5 years, is there sufficient evidence to support the organization's belief at the 0.05 level of significance? So what we're asking is 61.5 years of age significantly different than 61? Okay, so again, remember our first thing is that we're going to state our hypothesis, both our null and our alternative. So kind of the big sentence here that we want to pay attention to in that entire paragraph is that the Women's Rights Organization believes that this value does not accurately depict the current trends. So notice that they didn't say they believed it was lower or they believed it was higher. They just said we don't think it's accurate. So when we do something like that, that's indicating a two-tailed test because we didn't give a direction. We didn't say it was greater. We didn't say it was lower. We just said it's not. We just don't think it's right. So anytime we kind of do that where we don't talk about a direction, then that automatically gears us towards a two-tailed test. And so our null hypothesis is going to be that our mu is equal to 61. Remember, 61 was the age that the magazine reported the retirement at. That's going to be our population mean. And then our alternative would be that mu does not equal that 61 years of age of retirement. So that's what we're trying to determine if there is a difference. So the next thing we need to do is we need to determine our critical regions. Now again, we're going to be using a z-test. So our critical regions for a z-test never really change. So what I want you to do is write down this chart. So we have our alpha levels here on the first column. Alpha level of 0.05, 0.01, 0.05, 0.1, 0.15, and 0.2. Very rarely will you ever go past 0.1. You can do alpha levels at 15 and 20. The problem is that when you start getting that big of a alpha level, your statistic isn't very strong. Okay, so we want to try to keep fairly low on our alpha level. The most common is probably the 0.05. You occasionally get the 0.01 as an alpha level as well. Just kind of know that. The second column are the z-values for a two-tailed test. Now you'll notice that all of the z-values are positive on this chart. Remember, for a two-tailed test, you will have both the positive and the negative z-value of that. And then the last column is our one-tailed t-test. And again, directional wise, you'll need to remember what direction you're going. So if I'm saying that the values are lower, then they would all be negative. If I'm saying the values are going to be higher, then they would all be positive. One thing you can do to kind of help you on that is to draw out a really quick bell-shaped graph and shade where you think that critical region should lie. So for us, remember in our problem, it said it wanted it to be, we're going to do a two-tailed test since we didn't give a direction. We said I want our level of significance, which is our alpha level, at 0.05. So that means that we are going to use 1.96 as our critical score. But again, remember, for a critical score, since we're not doing direction, we have to do both negative 1.96 and a positive 1.96. So what we're saying is if my z-score that I'm going to compute here in just a second falls below negative 1.96 or falls above a positive 1.96, I am going to have enough evidence to reject my null hypothesis. So you can kind of see in the picture where my areas are. So any z-score that falls lower than negative 1.96 or falls higher than a positive 1.96 is my critical region. Now conversely, that means that if anything that falls in between these two values, so anything here in the non-shaded regions, would be that we would fail to reject our null hypothesis, that we don't have enough evidence to show that it's really different. Okay, so we've got our critical values, we've stated our alternative hypothesis. Now it's time to actually compute our z-score. And we are going to be using the z-score for sample means, the one that we determined in chapter 7, okay, where we divide not just by the standard deviation, but the standard error. Okay, so we have the mean minus the population mean divided by the standard error. So we need a couple pieces of information. Starting off, we need the standard deviation and the sample size. So if we go back through and read our problem, notice it told us the standard deviation was 2.5 years. And we were using a simple random sample of 95. So when we compute that, we're going to do 2.5 divided by the square root of 95. And that's going to give us 0.256. Okay, so now we're going to do our z-score. We need our sample mean, which is going to be what we think, which is the mean of the 95 people we talked to, and we need the mean of that the population thinks, or the national magazine thinks what they have is 61. So we're going to do our z-score, 61.5. Again, that's the mean from the sample minus the population mean of 61 divided by our standard error of 0.256. So that's going to give us 0.5 divided by 0.256, which is going to give us a 1.95 as a z-score. So now we've stated our hypothesis, we figured out our critical regions, we've got our z-score, so the last thing we need to do is we need to make a decision. Are we rejecting the null hypothesis, or are we not able to reject the null hypothesis? So I want you to remember our critical value was a plus or minus 1.96. So if it was bigger than 1.96 or less than a negative 1.96, we got to reject our null. But remember, for us, our score came out to be a positive 1.95. Now, although that is very, very close to our 1.96, it is still not greater than 1.96. So we would fail to reject the null hypothesis. In other words, at a 0.05 significance level, there is not sufficient evidence to support the claim that the average retirement age of women executives is not 61. So basically we're saying the magazine's probably right. We don't have enough evidence to show that our sample was different enough from what the population, what the magazine got to say that we think that they were wrong. Okay. Again, this is a two-tailed test. We're going to do a one-tailed test here in just a second to show you what that looks like.